Welcome to our STM32F4 workshop. My name is Ralf Kopsch. I'm Senior Applications Engineer at Keil, and I will create a USB host application that reads data from a USB memory stick and displays it on a touchscreen. Well, let me give you an impression of the final application. I have connected the USB memory stick to the USB host interface of my evaluation kit. The USB memory stick contains a text file, and by pressing a button on the touchscreen, the content of this file is displayed. Most parts of the application are created using pre-built software components shown on this slide. These components are configurable, and user code templates help you to add the application-specific functionality. As we go through the example, I will explain each of these components in more detail. The tool installation is explained in Application Note 268. And at this point, the Keil MDK and a software pack for the STM32F4 board is installed. For testing on hardware, you should also connect the ST Discovery Kit. To start with the project, open Microvision. Select Project and New Microvision Project. Create a suitable folder and enter the name of our project, in this case USB. Now select the microcontroller device you are using. The Discovery Kit uses the STM32F429ZIT-X. Then the Runtime Environment window opens where I can choose software components. Every project needs a startup code that initializes the device. This component is available under Device. Now the validation output shows that I need additional components that are needed by my selection. In this case, it is the CMSIS core. Once selected, the message disappears, which indicates correct component selections. Most devices provide today additional hardware abstraction layers that are also listed under the device component. The STM32 Hall is a list of available drivers for my device. And we are going to use this hall, which requires a framework. I select therefore the STM32 Classic framework. Again, this selection requires additional components that I may choose manually. But the RTE window offers a Resolve button, and once I click this button, requested components are automatically selected for me. This component selection adds files to my project, which are shown in the project window. Each component class has an own group, which makes it easy to identify the related files. Now you can start up implementing the application-specific code. Again, the software components help you here also, since most of them come with user code templates. To add such a user code template, right-click on the source file group and select Add New Item. Then choose User Code Template and the software component, in this case, Device. Here I can see all templates that belong to the device, for example, to implement exception handlers or interrupts. But every C program starts with a main module, and therefore I select this template. This adds the main.c module to your project, and you may now take a close look to that file. It initializes already the hall and configures the clock system. However, this clock system needs to know the clock source. The configuration, which is explained in detail at the STM documentation, needs compiler-defined settings. Therefore, I open the Options for Target C++ tab, where I enter the relevant symbols. For the external Xtel that we are going to use, the HSE value represents the crystal frequency. The ST Discovery Kit comes with an onboard debug adapter called ST-Link. Select this debug adapter under the Debug tab and open the Settings dialog. In this dialog, various parameters of that debug adapter are shown. The information under debug adapter indicates that the ST-link is connected to my system. For debug communication, the serial wire port is used. Once selected, the device is also shown in this dialog. The Trace tab allows me to configure trace information, but at this time I only enter the core clock of my device, which is running at 168 MHz. This configuration is used to show the execution time in the debugger. At the Flash Download tab, you can review the settings for flash programming. Here, the algorithm of the 2 MB on-chip flash is pre-selected based on my device selection. This completes the configuration of my development tools. Okay, let's generate our application, which at this moment is just the startup code, the hardware abstraction layer for the ST device, and an empty main routine. The build output window informs me about potential errors. Once the application is generated, I can program the image to the discovery kit. Now we can enter the debugger to verify the application. The system stops inside the main function, and I can single step through my code. The debugger offers various windows for analysis. Let me show how you can view variables in a watch window. Each Cortex system has got a variable called System Core Clock, which represents the core clock frequency of the Cortex-M device. By default, this is shown as hex value, but you can easily select the decimal format. Oh, I recognize the content is not matching the 168 MHz. Once I execute the system clock configuration, the value changes, and now the system core clock is configured properly. Now my application executes the empty while loop in main, and this completes our first step. Thanks for watching this video. In the next video I will show you how to add an RTOS kernel.